We now have middleware that generates e-tags. In this demo, we'll see how the validation model works with those. I restarted the application so the cache store is empty. Let's send that request to get a course again. We get back the response with the response headers we'd expect. If a response is stale, we learned that a cache must validate it, preferably using e-tags. So what we have to do, as we learned in the previous module, is add that e-tag as the if non-match header. So let's do that. And let's send the request again. We get back a 304 not modified. If you look at the console output window, we see that the last time the e-tag was generated matches the moment of the initial response. So, the second time we sent the request, the marvin.cache.headers middleware wasn't hit anymore. That means that it's the cache store that served up the response. So, even though the response cache attribute cannot generate e-tags, the response caching cache store does know how to interpret them and how to return a 304. This is good for performance. But there's a problem with this. As we learned, it's up to the cache to send the request to our application to validate its cached response. It's thus the cache that needs to set that if non-match header and check with the origin server, in other words, with our application. It is then up to our application to potentially return that 304 not modified, and up to the cache to respond by potentially returning the cached response. And that is different from what we just did. In our example, it was the client, Postman, that passed through that header. Not all caches are implemented the same, nor do they all correctly implement the validation model. Microsoft's response cache is an example of that. It's good for simple use cases that only deal with expiration. But once validation comes into play, it's not a good choice. That being said, our application would correctly respond, because the marvin.cache.headers middleware takes care of that. Let's give that a try. In the startup helper extensions, let's comment out the response caching cache store. And let's give this another try. Let's start again. Let's send the request to get one specific course without passing through an if non-match header. We get back the response with the headers we'd expect. Here's our e-tag. We're now going to mimic what a correct cache store should do. We're going to add that e-tag value as the if non-match header. Interesting fact here, the e-tag is exactly the same as it was previously. That's because e-tags are generated from the responses. The response in this case would be the same as it previously was, resulting in the same e-tag. Anyway, let's send this request. And we get back a 304 not modified. As we learn on the slides, this tells the cache that it can still use the cached response, so the body doesn't have to be regenerated, again improving performance. Now let's update that course by sending a put request. The response body has now been modified. Then let's send that get request with the if non-match header again. This time validation should fail. The e-tags won't match anymore, as the response body is taken into account when generating the e-tag. And this time we don't get back a 304 not modified. We get back a 200 OK. The response thus gets regenerated. And that is how the validation model works. So, the response caching middleware is not a great cache store for anything but simple use cases. What are the alternatives then? Let's have a look. As is probably clear by now, true HTTP caching isn't a simple subject, and not all cache stores behave as you might expect. In fact, in real life, most cache stores aren't just a piece of middleware like Microsoft's response caching middleware. They are actually full-blown cache servers that often require deep knowledge of how to configure them. Let's start with private caches. Those live at the level of the client, so those are a bit easier typically. Now, implementing this is out of scope for this course as we are working on the server. We are not building a client application, we're building the API. Yet, if you are building client-side applications in .NET Core, like a UWP or WPF app, you will probably want one of those. A good example is cashcow.client. You can find that via the link on screen. Shared caches are gateway or proxy caches. As mentioned, these are often full-blown servers you'd place right in front of your API. A few household names are Varnish, Apache Traffic Server, and Squid, but there's others as well. Each one of these correctly implements the HTTP cache standard, both the expiration and validation models. Combine this with the response cache attribute from the previous module if you only need the expiration model, or with marvin.cache.headers if you need expiration and validation. And you're good to go. But setting up such a server isn't easy. There's another option, a CDN or Content Delivery Network. That is a system of distributed servers that delivers pages and other web content to a user, based on the geographic locations of the user, the origin of the web page, and or the origin of the content delivery server. Simply put, it's a network of servers geographically distributed that speed up requests and related response delivery by ensuring that those requests are routed to the server closest to where you are. We don't notice it anymore, but a lot, if not most, of the internet runs on various CDNs. It's these CDNs that ensure that popular sites can load fast anywhere in the world. But being close to the user is just one of the things they do. That alone would not speed up the request response cycle as much. Next to proximity, CDNs also extensively use caching, HTTP cache to be precise. In fact, most of them will use cache servers like the ones we just learned about. The good thing is that using such a CDN means we no longer have to go through the often difficult setup of a cache server. Instead, they're provided out of the box and can often be configured via a simple user interface. A few examples are Azure CDN, Cloudflare, and Akamai. A disadvantage is obviously cost. If you expect to cache a lot of responses, expect to pay for it. The cache servers we talked about are often open source and free to use. So, if I can offer a piece of advice, don't implement the cache store at application level. Just ensure that your API can return cache control headers and supports expiration and/or validation models. A well-implemented cache store will correctly react to those. In other words, we're done as far as our API is concerned. For such a cache store, use one of the cache servers we just talked about, or make your life easier and use a content delivery network. The last piece of the puzzle is cache invalidation. Let's check that out. Cache invalidation essentially means wiping a response from the cache because you know it isn't the correct version anymore. A lot of this process happens automatically. A response is invalidated when it becomes stale, for example. Next to that, we've already seen how eTags help with this in the eTag demo. When a resource is updated, the eTag changes, which means the validation model ensures that a cache will return the correct new version. But sometimes resource manipulation has an effect on related resources. Take the courses resource, for example, a list of courses. If a put statement is sent to one course resource, that one course will get a new eTag. But the courses resource doesn't automatically change. If the course you just updated is one of the courses in the returned courses when fetching the courses resource, then the courses resource is out of date. Same goes for deleting a course. That too might have an effect on the courses resource. Automating something like that is not trivial. It is often a manual process, or a matter of implementing rules for related resources. This too is something CDNs can help with. In fact, if you read through their documentation, you'll notice they often pride themselves on allowing you to wipe something from their cache instantly, often via a web API call, sometimes even by providing an easy-to-use SDK. So, if you need functionality like that, CDNs are a good option. Most cache servers also offer this option. And if you ever have the need to do this with the marvin.cache.headers middleware, you can do so by calling mark for invalidation on an iValidator value invalidator implementing instance. Simply injecting iValidator value invalidator via constructor injection will get you the default implementation. And with that, let's have a look at this module summary. This module was focused on the validation model of the HTTP cache standard. For that, the best option is to use a strong validator like an ETAG. We added marvin.cache.headers to our API so ETAGs can be generated. By doing so, we ended up with an API that fully supports HTTP cache, which means it correctly generates headers, validators, and implements expiration and validation models so it can correctly respond when a cache sends a request. But we didn't have a cache store yet. The response caching middleware isn't a good option for anything but trivial cases. Shared cache stores are seldom something that you'd implement at application level. They are full-blown cache servers in their own right. Good options are Varnish, Apache Traffic Server, or Squid. Another option is using a CDN, which already implements one of those shared caches out of the box. Both of these often support manual cache invalidation, either via a remote API call, an SDK, or by allowing you to input rules for invalidation. Next to being used for validating a cache item, there's another interesting use case for ETAGs, dealing with concurrency. That's what we'll learn about in the next module.